Welcome to ALP Chemistry on Video, and this lesson is for Chapter 13 of Zumdahl on gases. And the first thing that I want to review with you are the three gas laws. Just to mention for those of you watching on video, this is a live recording, so you may hear me asking questions of and talking to Tamara, who's in class today with me. So the three gas laws, there's Boyle's law, Charles' law, and Avogadro's law. And you don't have to know these in great detail. What I do want you to know is the names of the laws and what they are in relation to. So Boyle's law is pressure and volume. Charles' law is volume and temperature. And Avogadro's law is volume in moles. Avogadro's law is probably the easiest one to remember, because if you think of Avogadro's number, the 6.02 times 10 to the 23, which is a mole. So if you think of Avogadro's number, then you know this one's about moles. So it's volume in moles. The way to remember the other two, the little memory trick I have for remembering these two, if you think about Boyle's law and you think about boiling peas, pressure, so that's one way you can remember Boyle's law. And Charles' law, you think about Charles being a very upper class name, and Charles and his tea, and wants the temperature of his tea to be just right. So Charles and his tea. So volume and temperature. So boiling peas for pressure and volume, and Charles and his tea for temperature and volume, and Avogadro's law is moles and volume. A little bit on each one. Boyle's law, the relationship between pressure and volume, and that means holding temperature constant and moles constant, because if you start changing temperature, temperature affects pressure and volume. So if you don't hold the temperature constant, that could be changing at the same time, and so Boyle's law won't work in that case. So you have to keep the temperature constant. An example of Boyle's law is if you had a piston, a sealed piston, where you have a certain pressure and a certain volume, and then if you increase the pressure and reduce the volume, you're going to reduce that volume, you have to use an increased pressure to do it. So you'll need more pressure if you want to increase the volume, because the gas is going to push against you and resist that change. If you were to plot pressure and volume, what that would look like is that as you reduce the volume, so as you go from right to left, as the volume gets smaller, the pressure gets bigger. That's the idea. As you squeeze it in, then it resists. So it's like if you had a balloon in your hand and you're trying to squeeze the balloon to make it smaller, it's going to resist your squeeze. And in chemistry, scientists and chemists in particular like straight lines, like linear graphs, because if you have a linear graph, then you can use linear functions, linear mathematical functions, which make calculation easier. And so what it turns out is that pressure is proportional to 1 over the volume. So as the volume goes up, 1 over the volume goes down, and the pressure goes down. So pressure and volume are oppositely related. As the volume goes down, 1 over V will go up. So if the volume goes down, I've lost my train of thought. Volume goes down. So as volume goes down, pressure goes up. That's right. As you decrease the volume, pressure goes up. So if you decrease the volume, then you're increasing 1 over V, and then the pressure goes up. And if the mathematical expression for this is that P is the pressure is equal to a constant times 1 over the volume, the constant being the slope of that line. And turns out that constant varies depending on temperature, depending on the number of moles you're dealing with. That it's constant for a given set of conditions. And you can express that as PV equals K. You don't have to worry about the details of this. Just the main thing I want you to know is that Boyle's law is the relationship between pressure and volume, and as volume goes up, pressure goes down. It's an opposite relationship. Charles' law, remember Charles and his tea, the temperature, likes the temperature of his tea. Relationship between volume and temperature at constant pressure. Because if you were to change the pressure while you're changing the volume and the temperature, that is going to affect things as well. So in order to see Charles' law at work, you have to hold the pressure constant. And what that looks like is that if you change the temperature, the volume will change, and basically increasing the temperature increases the volume. So there's a linear relationship, direct linear relationship. So volume decreases with temperature in a linear relationship to the boiling point. So basically, if you were to do an experiment where you started with a gas at a particular temperature and you measured its volume and you reduce the temperature, you're going to reduce the volume. And you reduce the temperature some more, you'll reduce the volume again. Eventually, you're going to hit the boiling point. And at the boiling point, the gas is going to turn into a liquid. At that point, you can't do the experiment anymore because you're no longer dealing with the gas. So it won't contract the same way a gas does. When you now have a liquid, the relationship isn't linear like it is with Charles' law. So you have to stop the experiment when you get to the boiling point, but you could extrapolate the line. So you can't get any more data points, but you can just extend the line that you've already started. And if you extend that line, it turns out that they all arrive at the same point, and this temperature is called absolute zero. And absolute zero is minus 273 degrees Celsius. And this temperature is defined as 0 Kelvin or 0 K. And Kelvin temperature, they don't use degrees, they just call it kelvins. But a Kelvin is the same as a degree, same size as a degree. So you can't actually measure absolute zero because gases will turn into a liquid before they get there. So you have to estimate it by extending the line, the experimental line. And this is very important when you're doing calculations involving gases, which you're going to be doing a lot of in this chapter. Always use Kelvin temperature. So you always have to take the temperature, if it's given in degrees Celsius, and convert to kelvins. And that's just either adding, that would be adding 273 to convert from Celsius to Kelvin, to the temperature. So if you're given a temperature in Celsius, add 273 to convert to kelvins. And mathematically, we would express this equation as volume equals a constant times the temperature. Again, this constant is constant for a given set of conditions. Or you could rearrange it like that.
So what number goes in there? Like that would be your time. No.
What number goes where in the constant? The constant will be the slope of this graph, and it varies with temperature. So it's constant, but it's only constant for a given set of conditions. So for a given pressure and a given number of moles, if you hold those things constant, the Boyle's law, the Charles law constant will stay the same. But if you change the pressure or change the number of moles, then the constant will change. So it's constant for a given set of conditions, but if you change the conditions, then it will change.
But that number will be in our...
No, you won't find that number in a table anywhere because it's a number that changes with the
No, but like
conditions.
If we're doing, like if you've got a question, that number will be there for us to put in.
You won't do any calculations using Charles' law. No. Your calculations are going to involve two other equations, which I'll show you shortly. Okay. So that was Boyle's law and Charles' law, and now Avogadro's law. Avogadro's law being the relationship between volume and moles. And again, you have to hold other things constant, pressure and temperature. And again, this law can be expressed as an equation. Volume equals a constant times moles. And again, that constant is constant only for a given set of conditions. Now, as far as doing the calculations go, this goes to Tamara's question about what number you would use as a constant for doing your calculations. The problem with all these three laws is that the constants change given different set of conditions. So what scientists wanted was a constant that would stay the same, and they also want one equation which will cover everything, and that is the ideal gas law. So this is one of the equations you're going to be doing for your gas law problems. The ideal gas law combines all three of those gas laws into one equation. And the equation is PV equals nRT, P and V being pressure and volume, N being moles, R being a constant, and T being temperature. And R is given a number of different names. The universal gas constant, the molar gas constant, often just called the gas constant. And this constant is constant no matter what the conditions. So whereas the other gas law constants, you change the conditions, the constants change. This one doesn't. So this one you will find in tables. And in fact, it's on the back of the black periodic table. You'll look there and you'll see that it is there.
So that's the number you use.
So you're going to use this number in your equation, and depends what units you're working with. And I think pretty much all the problems you'll be dealing with are going to be in atmospheres, so it'll probably be the 0.082058 number that you're going to use, and that has units of atmospheres times liters over moles times kelvins. If you change the units, the number will change. So if you use pressure units of pascals and volume of meters cubed, it will be 8.31451.
Now, do we have to memorize that?
You don't have to memorize this number. No. You'll be given it, although you may have it memorized because you'll use it enough. And if you change kilopascals, change to units of kilopascals and liters, it'll be the same, 8.31451. Use this equation when you have one gas under a single set of conditions. So if the problem only gives you one gas, one set of conditions, that's when you use the ideal gas law. There will also be some problems where they will change the conditions. So the problem will say you're given a particular gas under these set of conditions, and then you change the temperature. What will the new pressure be, for example? If you've got that kind of problem, where you have a before and an after, then this is the equation. And this equation actually comes out of the ideal gas law equation. And it's P1V1 over N1T1 equals P2V2 over N2T2. So you use this equation when conditions change. And again, when you use this equation and you're using temperature, temperature should be in kelvins. If some conditions are constant, you can eliminate them, which makes things easier. So for example, if in a particular problem the moles and the temperature are not changing, then you can eliminate them. And the reason you can eliminate them is because they're the same on both sides of the equation. So, you know, if it's 1 mole on the left side and 1 mole on the right side, you can multiply both sides by 1 mole and that will get rid of it. It'll be equal to 1. So, and the same thing with the temperature. If the temperature was 273 Kelvin on one side and 273 Kelvin on the other side, then you could multiply both sides by 273 Kelvin and that number would disappear. So that's why you can just eliminate those. And so all you'd be left with in this case would be P1V1 equals P2V2, which reduces the complexity of the equation. And before we get to some examples, there is a set of conditions which is abbreviated STP, which stands for standard temperature and pressure. And the standard temperature is 0 degrees Celsius. The standard pressure is 1 atmosphere. So if you ever see a problem where they say you have a gas under conditions of STP or a gas at STP, then you'll know it's exactly 1 atmosphere and exactly 0 degrees Celsius, which will be 273 kelvins, and in fact it's exactly 273.15 kelvins. Okay, so here we've got our first example problem. So here we have hydrogen gas at 63 degrees Celsius with a volume of 365 liters and pressure of 4.55 atmospheres. And this gas is changed to a pressure of 2.75 atmospheres and negative 35 degrees Celsius. And we want to calculate the new volume in atmospheres. So it's a very complicated problem. So the first thing you want to do is simplify it by decoding it and summarize the problem. And what I've drawn here is 2 circles which represent containers or balloons, and what we'll do is put the conditions of the gas in both balloons. So you're starting with hydrogen gas. And it has a volume of 365 liters and pressure of 4.55 atmospheres and 63 degrees Celsius. Oh, and it's 63 degrees Celsius. Missed that. Thought I was missing something. And it's changed to 2.75 atmospheres and negative 35 degrees Celsius. And the question is asking for the new volume. So does that make sense as far as summarizing the problem? And that simplifies it a lot. Once you've taken the problem apart and simplified it, summarized it for you. Now, there are 2 equations which you have a choice of using. One's the ideal gas law, PV equals nRT, or the combined gas law, P1V1 over N1T1 equals P2V2 over N2 T2, and you have to decide which one to use. So if you have a single gas under a single set of conditions, you use PV equals nRT. If you have a problem where conditions are changing, it's P1 V1 over N1 T1 equals P2 V2 over N2 T2, which is the second one, correct. So here we have conditions changing, so because conditions are changing, we need to use this equation. So we need to identify all the quantities. So 365 liters is the volume before things have changed, so that would be V1. 4.55 atm is the initial pressure, so that will be P1, and 63 degrees Celsius will be T1. The new volume will be volume 2. The new pressure is P2, and the new temperature is T2. And you notice the problem hasn't given any information about the moles, so we're going to assume that the moles aren't changing. And if the moles aren't changing, we can eliminate them from the problem. So the equation now becomes P1 V1 over T1 equals P2 V2 over T2. What we're trying to solve for is V2. So we need to rearrange the equation for V2. So we could plug the numbers in first or rearrange it first. Let's rearrange it first. So V2 is on top. It's okay where it is. If we move it to the other side, it'll end up being 1 over V2. We don't want 1 over V2, we want V2. So V2 we don't have to move. P1, V1, and T1 are already on the other side of the equal sign from V2, so they don't have to move. What we're going to have to move are P2 and T2. So let's write the equation first with the things that don't have to move. V2 is on top. Sorry, it's V2, not P2 that we want. Hello, there we go. It's V2 we want. Oh, computer's having some issues. That's better. So it's V2 we want. So we have to move P2. P2's on top. Where's it going to go when we move it? On the bottom. And T2 is on the bottom. Where's it going to go when we move it across? On the top. Now I'm going to move things around a little bit, and I'm going to put V2 on the left just so we can read right to left. And then what I'm going to do is I'm going to make it so that the P's and the T's are over top of one another. You don't have to do this, it's just going to make it easier to see what's going on. So it's going to be V1 times P1 over P2 and T2 over T1. So again, you don't have to rearrange it this way. It would work out fine if you didn't. But it just makes it a little easier to see what's going on if you put them over top of each other. So now we can plug numbers in. So V1 was 365 liters. P1 was 4.55 ATM. And T1 was 63 degrees Celsius. And on the bottom we have,
I thought T1 was the strong ball.
oh, you're right, it is. My mistake. So it's T2 on top, which is minus 35 degrees Celsius. And P2 is 2.75 ATM. And it was 63 degrees Celsius. Now before we can do this calculation, there's something we're going to need to do. Very good. Change your temperatures to Kelvin. Because our calculations involving gases, temperature always has to be in Kelvin. So let's do that up here. So 63 degrees Celsius, add 273 to that. 336 kelvins. Okay, and add 273 to negative 35. Or take 273 and subtract 35 from it. 238 kelvins. So let's rewrite everything now. So it's 365 liters times 4.55 ATM times 238 kelvins over 2.75 ATM times 336 kelvins. Now because we've got the pressure units over top of each other, we can easily see that the atmospheres are canceling. And because the temperature units are over top of each other, we can easily see the kelvins canceling. And you can also see what effect things are having. So 4.55 over 2.75, that should be not quite 2. But that's going to increase the volume. And the 238 over the 336 should decrease the volume. So you're going to have an increase in volume times a decrease in volume. So that means the volume may not change very much. So when you put those over top of each other, put the pressures over top of each other and temperatures over top of each other, it helps you to kind of estimate what's going to happen with the volume. Okay, so now you can go ahead and do that calculation. You can do the whole calculation all at once. So 365 times 4.55 times 238 divide by 2.75 divide by 336.
But when you divide, you'd only divide once, and then you'd multiply the 275 and then multiply the 336, wouldn't you?
So Tamara's question is, don't you multiply the 336? You'd have to put everything in brackets. If you want to do that, you have to put everything in brackets on the bottom. Everything on the bottom should be divided. Everything on the top should be multiplied. So if you do 365 times 4.55 times 238, divide by 2.75, divide by 336. If you don't divide by 336, if you do times 336, you're basically moving the 336 up to the top of the equation. Unless you put everything in the bottom in brackets.
So I get
427.768 liters, and is approximately equal to 3 sig figs.
So it'll be 428.
428 liters. Okay, the next example, we have, actually let's skip one and do this problem here. So this is the problem that starts with 5.00 mole of O2, and we'll come back to the next one, because I want to do a problem with a single gas under a single set of conditions, and then we'll come back to a change. So in this problem, you have 5.00 moles of O2, and it has a pressure of 1.25 atm at a temperature of 22 degrees Celsius. We want to know what the volume of the gas is. So in this problem, nothing's changing. It's a single gas, single set of conditions, and I've summarized it for you. We're starting with moles of 5.00 mole. Pressure is 1.25 atm, temperature is 22 degrees Celsius, and the question is asking us to get the volume. So we're going to use PV equals nRT, because that's the equation we use for single gas under single set of conditions. And the R value is 0.082058 liters times atmospheres over moles times Kelvin. So we need to rearrange PV equals nRT for V. So we want to get it in the form V equals, and what will that be?
nRT over P.
Good, nRT over P. The nRT doesn't have to move because it's already on the other side of the equal sign. The only thing that has to move is the P, and the P is on top on the left side, so it's going to go to the bottom on the right side. So now we can plug all the numbers in. So we have 5.00 mole times 0.08208 liters times atm over mole times kelvins times the temperature. And what do we need to do with the temperature? Change the kelvins. So 22 degrees Celsius is going to be equal to
295.
and so it's 273 plus 22 equals 295 kelvins. So the temperature is 295, and the pressure was 1.25 atm. And let's make sure that all our units are canceling properly. So moles will cancel with moles, kelvins will cancel with kelvins, atms will cancel with atms, and we'll be left with liters. And that's good because we want a volume unit. 96.8 to 844, which rounds to 3 sig figs.
So the
96.8 liters. Always make sure your units are canceling properly. You always should do that anyway. But make sure when you're doing these problems, because you may be given a pressure, say in pascals or pounds per square inch, and you may have to convert to atmospheres before you do the rest of the calculation. Okay, so that was a single gas under a single set of conditions. And let's go back up one again to a change. Maybe we should let's do another single gas under a single set of conditions. So let's go do the next one after the problem we just did, since we're on that roll of single gas under a single set of conditions. In this one we have 0.250 mole of argon, and it has a volume of 9.00 liters and pressure of 875 millimeters of mercury. What is the temperature in Kelvin and degrees Celsius? So I've summarized all the information, made a little balloon with all our information in it. We have a volume of 9.00 liters. Our moles is 0.250. Temperature we don't know, and the pressure is 875 millimeters of mercury. And again, we don't have changing conditions, so because we don't have changing conditions, we have to use PV equals nRT. What variable are we trying to solve for? T. So we need to rearrange this equation for T. So what do we have to move? We don't have to move the T. T is fine where it is. The N and the R. So we have to move N and R. So PV can stay where it is. T can stay where it is. Where did the N and R go? On the bottom. Because they were on top. When we move to the other side of the equal sign, they go on the bottom. So T equals PV over NR equals 875 millimeters of mercury times 9.00 liters divide by 0.250 moles times 0.08258 liters ATM over mole times Kelvin. And at this point, Tamara's smiling. What are you smiling about, Tamara?
I don't have enough room.
Oh, you're running out of room. Okay. Before you do the calculation, don't do the calculation yet. Look at your units and tell me if you see any issues with the units.
You don't have anything to cancel the ATM and the MM of
Right. There's nothing to calculate the millimeters of mercury. That's a pressure unit. There's nothing to calculate the millimeters of mercury and the atmospheres. So we need to change the units. And what we need to do is convert millimeters of mercury to atmospheres. And that's something that you'll have to look up the conversion for. And
So is that something we do on a
So Tamara's question is, would that be something you would do on your periodic table? It's not on your periodic table, but if you have the black periodic table from the bookstore, if you turn it over, you'll see that there is a section for pressure, and if you read across, it gives the equivalent units for pressure. So 1 atmosphere equals so much. And it turns out that we need millimeters of mercury on the bottom. We need atmospheres on top because we want atmospheres. And there are 760 millimeters of mercury in 1 atmosphere. So 1 atmosphere is 760 millimeters of mercury.
So
1.1513 ATM, and that should be rounded to 1.15 ATM for 3 sig figs. And in your book, having read the chapter, there's a section on pressure, and it talks about what pressure is and the pressure units. And this unit, 760 millimeters of mercury, is also called a torr because the barometer, which is used to measure atmospheric pressure, was invented by a guy by the name of Torricelli. So the millimeter of mercury was named a torr in honor of him. You don't have to memorize that, but because again, you'll have that given to you. But you probably will end up having it memorized. Had to pause for a moment because I was having a coughing fit for those of you watching on video. Okay, so now we can rewrite this equation with the atmospheres unit in. So 1.15 ATM times 9.00 liters over 0.250 mole times 0.082058 liters ATM over mole times Kelvin. And checking our units, atmospheres cancel, liters cancel, moles cancel, and what we're left with is kelvins, and the kelvins are left in the denominator of a denominator, and if you have a unit in the denominator of a denominator, it bounces back up to the numerator. So our answer is in kelvins, which is good, because we want an answer in temperature units. $504.521,
yeah.
and that's approximately equal to should be 3 sig figs. 505. So we've done a couple of problems where we've had a single gas. Let's go back now. we'll go back a couple of pages and do a problem where we're changing conditions. So you have a cylinder containing CO2 gas at a temperature of 298 kelvins and a pressure of 1.00 atm. You increase the pressure to 10.0 atm. If the original volume was 2.00 liters, what is the new volume? The temperature and the number of moles is not changing. And I've diagrammed this out below. So we're starting out with a pressure of 1.00 atm, volume of 2.00 liters, and temperature of 298 Kelvin. We're increasing the pressure to 10.0 atm, and we want the new volume. The temperature isn't changing, and it's a closed system. The moles aren't changing either. So it's changing conditions. So if it's changing conditions, what equation do we use? P1V1 over N1T1 equals the P2V2 over N2T2. And the temperature isn't changing, so we can eliminate that. And the moles aren't changing, so we can eliminate that. So what we're left with is P1V1 equals P2V2. And what is it that we're trying to get? We're trying to get V2. So what do we have to move to get V2? Just the P2. The P1V1 is okay where it is because it's already on the opposite side of the equal sign. So we just have to move the P2. And where's the P2 going to go? Top or bottom on the left side? Bottom. Because it was on the top on the right side, it's going to go to the bottom on the left. And I'm just going to rearrange it so that the V2 is on the left side. So it's equal to, so P1 was 1.00 atm. And V1 was 2.00 liters. And P2 is 10.0 atm. And looking at our units, ATMs will cancel, leaving us with liters, which is good because we should end up with a volume unit. And we can see that the effect of changing the pressure should be to decrease the volume. Because it's 1 over 10, 1 atmosphere over 10 atmospheres. So 0.2, and how many sig figs should we have? Should have 3 sig figs. 3 sig figs is correct. Yep.
So we'd have to put 2 more zeros.
So correct. We have to put 2 more zeros to make it 3 sig figs because the leading zero doesn't count. Okay, we can go back down now. Dalton's law of partial pressures. I think before we do Dalton's law, I'm just looking ahead here. Before we do Dalton's law, I just want to go back and talk about the ideal gas law for a moment. Here. There's some assumptions that go along with the ideal gas law. And if you assume that a gas is behaving ideally, there are some things that go along with that. One of the things that go along with that is that all gases are considered to be identical. So it doesn't matter whether you're dealing with oxygen or carbon dioxide or helium. We're assuming that they're going to behave the same. The other thing is that we assume that we can freely contract and freely expand the gas. And the consequence of that is that there's an assumption that the gases don't have any volume. Because if they had volume, if you put if you pressure on them so that they start bouncing off each other, they're going to resist the increase in pressure, and that would that will change the effect of pressure on volume. Also, if the gases molecules can stick to each other, then they won't freely expand either. Because if you were to increase the volume, the gas molecules should freely expand to fill that volume. What might happen is they might stick together and they might resist that expansion. So the assumptions that go with the ideal gas law is that all gases are the same, behave the same way. We assume they don't have volume, and we assume that they don't stick together. So it turns out that the ideal gas law is really an approximation, because in reality gases do have volume, and big gas molecules will behave different from little gas molecules. Gas molecules that are sticky will behave differently from gas molecules that aren't. So so the ideal gas law is really an approximation. The conditions where the ideal gas law works best and gives a better approximation are conditions where the pressure is low, because if the pressure is low, the gas molecules are far apart, they're not packed together, and so the volume of the gas molecules themselves doesn't come into play. And also they're far enough apart that they're not sticking together that much. And the other condition is high temperature, because if the temperature is high, the gas molecules or the gas particles are going to be moving very fast, and they'll move so fast that they don't have time to stick together. And so stickiness doesn't become an issue. So under low pressures and high temperatures, the ideal gas law tends to work best. And scientists have been trying to fine-tune the ideal gas law to make it more accurate. And what happens is they often end adding terms to the ideal gas law, and they keep adding these correction terms to correct for things like volume of the particles and the stickiness of the particles and things like that. So some of the corrections to the ideal gas law can get quite complicated as they try and get a better and better approximation. Okay, so we're going to move on to talk about Dalton's law of partial pressures, and it deals with mixtures of gases. And the ideal of Dalton's law is that the total pressure of a mixture of gases is just adding up the individual gases as if each one was independent of the other. It didn't know the others existed. And this goes back to that assumption that in the ideal gas law you assume that all gases are identical. So it doesn't matter what gases you're mixing together. You're assuming that they all behave the same, they behave exactly like each other, and one doesn't affect the other. So that means that you can just add up the pressures of all the individual gases to get the total pressure. And the pressures of the individual gases are called the partial pressures. Okay, so here is a practice problem. You have 0.50 atmospheres of helium, 0.25 atmospheres of argon, and 0.10 atmospheres of krypton. And we want to know what the total pressure is. So the total pressure should be just the sum of all the partial pressures. So it should be the sum of the pressure of helium the pressure of argon, and the pressure of krypton. So it should be 0.50 atm plus 0.25 atm plus 0.10 atm. And what did you get again, Tamara? 0.85 atm is correct. So that one was fairly straightforward. Here we have another mixture of gases. In this one we have 0.78 atmospheres of nitrogen, 0.21 atmospheres of oxygen, and CO2 at a total pressure of 1.00 atm. What's the partial pressure of the CO2? So let's summarize this question first. We have N2, and its partial pressure is 0.78 atm. We have O2, and its partial pressure is 0.21 atm. We have CO2, and we don't know its partial pressure. And we know the total pressure is 1 atmosphere. So we know that the total pressure, according to Dalton's law, should be equal to the nitrogen pressure, the oxygen pressure, and the carbon dioxide pressure added together. And it's the carbon dioxide pressure that we want. So how do we get the carbon dioxide pressure by itself? What do we have to move? The PN2 and the PO2. The P total is already on the other side of the equal sign, so we don't have to move that. We have to move the PN2 and the PO2. What's going to happen to them when we move them to the opposite side of the equation? They won't go underneath, because if they were multiplied, they would go underneath. But in this case, they're added. So when you move something to the opposite side of an equal sign, you kind of do the opposite. If it's multiplied, you divide it. If it's divided, you multiply it. If it's added, you subtract it. If it's subtracted, you multiply it. So these are added on the right side, so when you move them to the left, they're going to be subtracted. And let's just move things around so it's reading left to right. And what do you get when you do that? 0.01 ATM. Are the sig figs correct?
Um, yeah.
It's not a question of how many sig figs you should have in this case, because it's subtraction. So it's lining up the decimal point and finding the last significant place. And it is correct, because the last significant place should be the second decimal place to the right. So 0.01 ATM is correct. Okay, what have we got here? So 5 grams of helium is combined with 5 grams of neon. The container has a volume of 2.50 liters, and the temperature is 27 degrees Celsius. What's the total pressure? So let's summarize this problem. So we have 5.00 grams of helium. So let's say M of helium equals 5.00 grams. And we have 5.00 grams of neon. So the mass of neon, or M neon, is 5.00 grams. We know the volume is 2.50 liters. And the temperature is 27 degrees Celsius. And we want to find out the total pressure. So, any thoughts of how you would solve this? Well, we've been given mass, so Tamara's question is, why do we have M? We haven't been given N in this case, we've been given mass. So we're going to have to calculate N.
So it would be M1, M2?
It's not M1 and M2 in this case. It's a Dalton's law problem. So conditions aren't changing here. If conditions were changing, then it would be a combined gas law problem. Conditions aren't changing. We're dealing with a mixture of gases, but under a single set of conditions. So it's a Dalton's law problem because we have a mixture of gases. So the total pressure equals the pressure of the partial pressure of the gases added together. So what you'll need to do is calculate the partial pressure of each gas. So you're going to need to do PV equals nRT for each gas. And you want P, that means we have to move the V. So the P is going to be nRT over V, and we have to do that for both helium and neon. But before we can do that, we need N, which is the number of moles. So we're going to have to convert mass to moles, which is a GNP problem. So for helium, we need to take mass and convert to moles. So GNP, we've been given 5.00 grams. We need to get the number of moles. How many steps in that? Just one. So 5.00 grams times a line, and we want moles. Oops, didn't leave myself enough room here. And we need grams in the bottom, we need moles on top. And what's the grams per mole for helium? Looking at the periodic table on the wall, 4.0026. So 1 mole is 4.0026 grams.
So it'd be 1.249.
1.249, which is approximately equal to 1.25 mole. So that's our N. So now we can do PHE. PHE equals 1.25 mole. Oh, yeah, 1.25 mole times 0.082058 liters ATM over mole times Kelvin times the temperature, and the temperature was 27 degrees Celsius, and we have to add 273 to make that kelvins. 300, I think. 300 Kelvin, decimal, times 300 decimal kelvins over the volume, which was 2.50 liters. Checking our units, moles cancel, liters cancel, kelvins cancel, leaving us with ATM. $12.3087, which rounds to 12.3 ATM. So that's a pressure over helium. And now we need to do neon. So we have to do the same thing for neon. And we've run out of room on this page, so I'll have to go to a new page. You have to do the same thing for neon. And for neon, it is 20.18 grams per mole. So it's 1 mole over 20.18 grams. .24777, which is approximately equal to 0.248 moles. So now we have to do another pressure calculation for neon. So P equals nRT over V, which is equal to 0.248 mole times 0.08 2058 liters ATM over mole times Kelvin times 300 Kelvin divided by 2.50 liters.
Two point four four two
2.4420, and just checking the units, make sure our units are working. Moles cancel, liters cancel, kelvins cancel, leaving us with ATM. And then we need to round to the sig figs. 2.44 ATM is the pressure of the neon, and the total pressure is the pressure of the helium plus the neon. And our helium was 12.3 ATM. And our neon is 2.44 ATM. So that's equal to 14 point
Oh, no,
74 ATM, which rounds to
so that's the same, so it'd be
14.7, because the rule for addition is to round to the last significant place, which in this case is the 10th place. Now there is a way we could have simplified this problem a little.
Now you tell me.
Just a little, and that is by recognizing that for an ideal gas, all gases are considered to be the same. So in that case, it doesn't matter whether it's helium or neon. So once we've got the moles, we could have just added the moles together and gotten the total number of moles, and we still have to do the nRT over V, but we could use the total number of moles and just do that calculation once instead of having to do it twice. So we could have simplified things a little bit, but that's okay.
What do you mean produce this total number of moles?
Um,
Just,
we could have just, once we had calculated the moles of helium and the moles of neon, we could have just added those moles together and used the total number of moles to do the calculation once. Instead of having to do a separate partial pressure of helium and a separate partial pressure of neon, once we had the total number of moles, we could have calculated the total pressure in one nRT over V. And that would have worked out to give us the same number if we had done that. But it does require a little lateral thinking a little bit beyond. Okay, so the next thing is gas stoichiometry. And again, it's mole map stuff. This time, what you do is you can add PV and T to the mole map coming out of the N. N is sort of the central hub for everything. Everything comes off the ends. Once you've got your moles, you can then use the ideal gas law equation to calculate whatever you need to calculate, the pressure, the volume, or the temperature, whatever the question is asking you. So for example, let's say you have C3H8 plus 5O2 producing 3 CO2s and 4 H2Os. And let's say you start with 5.0 kilograms of C3H8, which is propane, which is the same as 5.0 times 10 to the 3 grams. And what the question wants is the volume of CO2 under conditions of 1 atmosphere, 400 degrees Celsius, which is the same as 673 Kelvin. So let's put this information on a mole map. The two substances we're calculating are C3H8 and CO2. The information that has been given is that we have 5.0 times 10 to the 3 grams of C3H8. We want the volume of CO2 for conditions of pressure equal to 1.000 atm and temperature of 673 kelvins. So to do this problem, you're going to need to go to moles of C3H8 to moles of CO2, and then you're going to have a separate calculation using the ideal gas law equation to get your volume. So you're going to have to do 3 calculations, or a 3-step calculation. Making sense?
Yes, I guess.
Yes, sort of.
Hoping there would be no more mole maps.
You're hoping for no more mole maps. Sorry to disappoint you.
Yeah.
So 5.0 times 10 to the 3 grams C3H8, and you'll have 2 lines, and the third step is going to be a separate calculation using the ideal gas law. So we need the moles of CO2, because we'll need that to go into the ideal gas law, because what we're going to be doing is N equals PV over RT. No, it's not. It isn't. We want volume. So volume equals nRT over P. That's what we'll need. So grams of C3H8 will go on the bottom. Moles of C3H8 will go on top. And then at the second step, we'll get rid of moles of C3H8 and we'll have moles of CO2. Oops, CO2. So we need the grams per mole for C3H8. So 3 times C, 8 times H, 3 times 12.011 8 times 1.00794. I think that's 36.033, I think. And that will be 8 point something.
That's 8.06352. .023, yep. It's 44.09652.
Which is approximately equal to 44.09652, which is approximately equal to
44.097.
44.097 grams per mole. And that number goes here. And then we need the moles of CO2 and moles of C3H8. And there are 3 CO2s for 1 C3H8. Tamara's still calculating away there. So it should be 5.0 EE3 divided by 44.097 times 3.
Sorry, that's 340.159. Or do you want more than that?
No, that's okay. And it should be 2 sig figs. But I think what we'll do is carry in this problem it won't make much difference, but carry an extra sig fig. So it should be 340 no decimal, but let's carry the extra. Actually, it won't matter in this case because it's just a 0. I was going to say carry the extra sig fig for the purposes of the calculation and then round it at the end, but it won't make a difference in this case because it's a 0 anyway. So 340 moles. Okay, so this will go into our ideal gas law equation. V equals nRT over P. So 340 moles times 0.08258 liters ATM over mole times Kelvin times the temperature, which is 673 kelvins, and divided by the pressure, which is 1.000 ATM. Checking our units, moles cancel, ATMs cancel, kelvins cancel, leaving us with liters.
So 18776.0 5115.
That's so 18776 liters is approximately equal to
3, so it'll be 18880.
how many sig figs do we have here?
Oh, just 2.
Just
So
2.
it'll be 119
19 what?
liters.
Nope.
No?
Nope. If someone owed you $18,776 and they said, okay, how about I give you $19?
Times 10 to 3.
Times 10 and 3, or just replace the numbers you're dropping with zeros. So remember to drop any numbers you're eliminating through rounding, replace with zeros. Otherwise the decimal point moves and you're changing the value of the number significantly. Okay, and here is another mole map problem. But I think I'll leave this one to you as a practice problem. I think you don't feel that we need to do this one, do you? It's another mole map problem.
No, not at all.
Do you want to do this one together?
No, that's all right.
You're okay with doing this for practice? So for those of you watching on video, give this problem a try, and if you have trouble with it, let me know and I'll give you a hand with it.